For centuries, we believed the universe was a sensible place. We assumed that things had definite properties whether we looked at them or not, and that nothing, no force, no signal, could travel faster than the speed of light. This was local realism, the bedrock of classical physics. But today, that bedrock has been completely dismantled. We are discovering that the universe is not locally real. Instead, it is held together by a phenomenon so strange that Albert Einstein famously dismissed it as spooky action at a distance. We are talking about quantum entanglement. It is no longer just a philosophical debate or a laboratory curiosity. In 2025, entanglement has become the literal fuel for a new era of technology, from unhackable global networks to computers that can solve problems in seconds that would take today's machines billions of years. Today, we unravel the mystery of entanglement and explore how it is redefining our understanding of reality, information, and the very fabric of space-time. To understand where we are going, we have to understand the fight that started it all. In 1935, Einstein and his colleagues Podolsky and Rosen published a paper that challenged the very foundations of quantum mechanics. This became known as the EPR paradox. Einstein couldn't accept that two particles could be so deeply linked that measuring one would instantaneously affect the other, regardless of the distance between them. He argued that if quantum mechanics were true, it would require a spooky connection that bypassed the speed of light. He believed there must be hidden variables, internal instructions the particles carried with them, that determined the results in advance. For 30 years, this remained a philosophical stalemate. That changed in 1964, when a theorist named John Stuart Bell came up with a mathematical way to test it. He proved that if Einstein was right and hidden variables existed, there was a limit to how correlated two particles could be. If quantum mechanics was right, that limit would be shattered. It took decades of experimental brilliance to settle the score. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for doing exactly that. Through a series of landmark experiments, they closed every logical loophole. They showed that when you measure an entangled particle, its partner decides its state instantly even if the two are kilometers apart. They proved once and for all that the universe is not locally real. Objects do not have definite properties until they are observed. This discovery wasn't just a win for quantum theory, it was the spark for the second quantum revolution. We moved from just observing these weird laws to actively engineering them. One of the most common myths about entanglement is that it allows for instantaneous communication, faster than light radio. But the laws of physics are clever. While the collapse of a particle's state is indeed instantaneous, we are bound by the no communication theorem. If Alice measures her particle, she gets a random result. Bob, on the other side of the galaxy, also sees a random result without a classical signal like a radio wave or a fiber optic pulse. To tell Bob what Alice saw, he has no way to decode the message. This means entanglement provides correlation without causation. However, it does enable something even more incredible: quantum teleportation. In teleportation, we aren't moving matter, we are moving the structure of information. By using an entangled pair as a bridge, we can erase the state of a particle in one location and have it reappear perfectly in another. Because this process requires a classical key to be sent at the speed of light, it doesn't violate relativity. But it does allow for a level of data fidelity that is impossible in our classical world. This is the core mechanism of the quantum internet we are building right now. As we move through 2025, the race for the quantum internet has moved from the lab into the real world. The biggest challenge has always been distance. In standard fiber optic cables, light fades over long distances. In the classical world, we use amplifiers. But in the quantum world, you cannot clone or amplify a state without destroying it. The solution: quantum repeaters and entanglement swapping. This is essentially teleporting entanglement itself. By entangling a series of intermediate nodes, we can link Alice and Bob even if they never interact directly. In late 2024 and throughout 2025, we've seen massive milestones. In New York City, the Gotham Q network has successfully deployed over 300 kilometers of commercial fiber that maintains entangled connections beneath the city's noisy streets. Globally, China's Misha satellite program has established the first intercontinental quantum key distribution link between Beijing and South Africa. Even Boeing is getting involved, testing entanglement sources on the International Space Station to prepare for a space-based quantum repeater network by 2026. These aren't just experiments, they are the first threads of a global, unhackable web. But entanglement isn't just about communication, it's the secret sauce of quantum computing. A classical computer uses bits, ones or zeros. A quantum computer uses qubits, which can exist in a superposition of both. But superposition alone isn't enough. It's entanglement that allows the computational power to scale exponentially. If you have a 50-qubit processor and those qubits are fully entangled, you are dealing with a state space that would require the memory of every classical computer on Earth combined to simulate. Entanglement allows algorithms like Shor's, which could crack the encryption protecting the entire internet, to work by creating a massive interference pattern. It's like a choir where every voice is perfectly synced. The algorithm uses entanglement to cancel out wrong answers and amplify the correct ones. Without entanglement, a quantum computer is just a very expensive, very cold classical machine. Perhaps the most mind-blowing realization of the last few years is that entanglement might be the very glue of the universe. Theoretical physicists are now looking at the holographic principle and the Ryu-Takanaji formula, which suggest a shocking connection between quantum information and geometry. There is a famous conjecture known as ER equals EPR. It proposes that Einstein-Rosen bridges, which we know as wormholes, are actually just the geometric manifestation of entanglement. In this view, two entangled particles are literally connected by a microscopic wormhole in the fabric of space-time. If this is true, then space itself is an emergent property. Hair and theory only exist because of the density of entanglement between quantum fields. If you could somehow unentangle a region of space from the rest of the universe, that space would simply cease to be connected to our geometry. It would pinch off. We even saw a hint of this in 2022 and 2023, when researchers at Google and Caltech used a quantum processor to simulate a traversable wormhole. While there is still a massive debate over whether they created gravity or just modeled it, the message is clear. The boundary between the subatomic world and the cosmic world of gravity is disappearing. We are living in the entangled era. What Einstein once called spooky is now the foundation of our most ambitious technologies and our deepest theories about existence. We've gone from questioning if entanglement was real to using it to teleport information, power supercomputers, and map the geometry of the vacuum. As we look toward the 2030s, the spooky connections of the quantum world will no longer be a mystery. They will be the infrastructure of our civilization. We are finally learning to weave the